Sets and historical counting systems. It is natural for us to clarify items into groups or sets and consider how those sets overlap with each other. We can use these sets, understand relationships between groups, and to analyze survey data. Basics. An art collector might own a collection of paintings, while a music lover might keep a collection of CDs. Any collection of items can form a set. Set. A set is a collection of distinct objects called elements of the set. A set can be defined by describing the contents or by listing the elements of the set enclosed in curly brackets. Example 1. Some examples of sets defined by describing the contents. A. The set of all even numbers. B. The set of all books written about travel to Chile. Some examples of sets defined by listing the elements of the set. A. The set of numbers 1, 3, 9, 12. B. The set of colors red, orange, yellow, green, blue, indigo, purple. A set simply specifies the contents. Order is not important. The set represented by numbers 1, 2, 3 is equivalent to the set of numbers 3, 1, 2. Notation. Commonly, we will use a variable to represent a set to make it easier to refer to that set later. The symbol element of means is an element of. A set that contains no elements, curly brackets, is called the empty set and is notated null set. Example 2. Let A equal 1, 2, 3, 4. To notate that 2 is the element of the set, we'd write 2 is an element of A. Sometimes a collection might not contain all the elements of a set. For example, Chris owns 3 Madonna albums. While Chris's collection is a set, we can also say it is a subset of the larger set of all Madonna albums. Subset. A subset of a set A is another set that contains only elements from the set A, but may not contain all the elements of A. If B is a subset of A, we write B is a subset of or equal to A. A proper subset is a subset that is not identical to the original set. It contains fewer elements. If B is a proper subset of A, we write B is a subset of A. Example 3. Consider these 3 sets. A equals the set of all even numbers. B equals the set of numbers 2, 4, 6. C equals the set of numbers 2, 3, 4, 6. Here, B is a subset of A since every element of B is also an even number. So is an element of A. More formally, we could say B is a subset of A since if X is an element of B, then X is an element of A. It is also true that B is a subset of C. C is not a subset of A since C contains an element, 3, that is not contained in A. Example 4. Suppose a set contains the plays Much Ado About Nothing, Macbeth, and A Midsummer's Night Dream. What is a larger set this might be a subset of? There are many possible answers here. One would be the set of plays by Shakespeare. This is also a subset of the set of all plays ever written. It is also a subset of all British literature. Union, intersection, and complement. Commonly, sets interact.
For example, you and a new roommate decide to have a house party and you both invite your circle of friends. At this party, two sets are being combined, though it might turn out that there are some friends that were in both sets. Union, intersection, and complement. The union of two sets contains all the elements contained in either set or both sets. The union is notated A union B. More formally, X is an element of A union B if X is an element of A or X is an element of B or both. The intersection of two sets contains only the elements that are in both sets. The intersection is notated A intersection B. More formally, X is an element of A intersection B if X is an element of A and X is an element of B. The complement of the set A contains everything that is not in the set A. The complement is notated A prime or A raised to the C power or sometimes tilde A. Example 5. Consider the sets. A equals the set of colors red, green, blue. B equals the set of colors red, yellow, orange. C equals the set of colors red, orange, yellow, green, blue, purple. Find A union B. The union contains all the elements in either set. A union B equals the set of colors red, green, blue, yellow, orange. Notice we only list red once, B. Find A intersection B. The intersection contains all the elements in both sets. A intersection B equals the color red. C. Find A to the C power intersection C. Here we're looking for all the elements that are not in set A and are also in C. A to the C power intersection C equals the set of colors orange, yellow, purple. Notice that in the example above, it would be hard to just ask for A to the C power since everything from the color fuchsia to puppies and peanut butter are included in the complement of the set. For this reason, complements are usually only used with intersections or when we have a universal set in place. Universal set. A universal set is a set that contains all the elements we are interested in. This would have to be defined by the context. A complement is relative to the universal set, so A to the C power contains all the elements in the universal set that are not in A. Example 6. A. If we were discussing searching for books, the universal set might be all the books in the library. B. If we were grouping your Facebook friends, the universal set would be all your Facebook friends. C. If you were working with sets of numbers, the universal set might be all whole numbers, all integers, or all real numbers. Example 7. Suppose the universal set is U equals all whole numbers from 1 to 9. If A equals the set of numbers 1, 2, 4, then A to the C power equals the set of numbers 3, 5, 6, 7, 8, 9. As we saw earlier with the expression A to the C power intersection C, set operations can be grouped together. Grouping symbols can be used like they are with arithmetic to force an order of operation. Venn diagrams. To visualize the intersection of sets, John Venn in 1880 thought to use overlapping circles, building on a similar idea used by Leonhard Euler in the 18th century. These illustrations are now called Venn diagrams. Venn diagram. A Venn diagram represents each set by a circle, usually drawn inside of a containing box representing the universal set. Overlapping areas indicate elements common to both sets. Basic Venn diagrams can illustrate the intersection of 2 or 3 sets. Example 9. Create Venn diagrams to illustrate A union B, A intersection B, and A to the C power intersection B. A union B contains all elements in either set. A intersection B contains only those elements in both sets in the overlap of the circles. A to the C will contain all elements not in the set A. A to the C intersection B will contain the elements in set B that are not in set A. Cardinality. Oftentimes we are interested in the number of items in a set or subset. This is called the cardinality of the set. Cardinality. The number of elements in a set is the cardinality of that set. The cardinality of the set A is often notated as the cardinality of A or N of A. Example 12. Let A equal the set of numbers 1, 2, 3, 4, 5, 6, and B equal the set of numbers 2, 4, 6, 8. What is the cardinality of B? A union B, A intersection B. The cardinality of B is 4, since there are 4 elements in the set. The cardinality of A union B is 7, since A union B equals the set of numbers 1, 2, 3, 4, 5, 6, 8, which contains 7 elements. The cardinality of A intersection B is 3, since A intersection B equals the set of numbers 2, 4, 6, which contains 3 elements. Cardinality properties. N of A union B equals N of A plus N of B minus N of A intersection B. N of A to the C equals N of U minus N of A. Notice that the first property can also be written in an equivalent form by solving for the cardinality of the intersection. N of A intersection B equals N of A plus N of B minus N of A union B. Historical counting systems. Introduction and basic number and counting systems. Introduction. As we begin our journey through the history of mathematics, one question to be asked is, where do we start? Depending on how you view mathematics or numbers, you could choose any of a number of launching points from which to begin. Howard Eves suggests the following list of possibilities. Where to start the study of the history of mathematics? At the first logical geometric proofs traditionally created to Thales of Miletus, 600 BCE, with the formulation of methods of measurement by the Egyptians and Mesopotamians, Babylonians, where prehistoric peoples made efforts to organize the concepts of size, shape, and number. In pre-human times, in the very simple number sense and pattern recognition that can be displayed by certain animals, birds, etc. Even before that, in the amazing relationships of numbers and shapes found in plants, and with the spiral nebulae, the natural course of planets, and other universe phenomena. We can choose no starting point at all and instead agree that mathematics has always existed and has simply been waiting in the wings for humans to discover. Each of these positions can be defended to some degree, and which one you adopt, if any, largely depends on your philosophical ideas about mathematics and numbers. Nevertheless, we need a starting point. Without passing judgment on the validity of any of these particular possibilities, we will choose as our starting point the emergence of the idea of number and the process of counting as our launching pad. This is done primarily as a practical matter given the nature of this course. In the following chapter, we will try to focus on 2 main ideas. The first will be an examination of basic number and counting systems and the symbols that we use for those numbers. We will look at our own modern, Western number system as well as those of a couple of selected civilizations to see the differences and diversity that is possible when humans start counting. The second idea we will look at will be base systems. By comparing our own base 10 decimal system with other bases, we will quickly become aware that the system that we are so used to, when slightly changed, will challenge our notions about numbers and what symbols for those numbers actually mean. Recognition of more versus less. The idea of numbers and the process of counting goes back far beyond when history began to be recorded. There is some archaeological evidence that suggests that humans were counting as far back as 50,000 years ago. However, we do not really know how this process started or developed over time.
The best we can do is to make a good guess as to how things progressed. It is probably not hard to believe that even the earliest humans had some sense of more and less. Even some small animals have been shown to have such a sense. For example, one naturalist tells of how we would secretly remove one egg each day from a plover's nest. The mother was diligent in laying an extra egg every day to make up for the missing egg. Some research has shown that hens can be trained to distinguish between even and odd numbers of pieces of food. With these sorts of findings in mind, it is not hard to conceive that early humans had, at least, a similar sense of more and less. However, our conjectures about how and when these ideas emerged among humans are simply that. Educated guesses based on our own assumptions of what might or could have been. The need for simple counting. As societies and humankind evolve, simply having a sense of more or less, even or odd, etc., would prove to be insufficient to meet the needs of everyday living. As tribes and groups formed, it became important to be able to know how many members were in the group and perhaps how many were in the enemy's camp. Certainly, it was important for them to know if the flock of sheep or other possessed animals were increasing or decreasing in size. Just how many of them do we have anyway is a question that we do not have a hard time imagining them asking themselves or each other. In order to count items such as animals, it is often conjectured that one of the earliest methods of doing so would be with tally sticks. These are objects used to track the number of items to be counted. With this method, each stick or pebble or whatever counting device being used represents one animal or object. This method uses the idea of one-to-one correspondence. In a one-to-one correspondence, items that are being counted are uniquely linked with some counting tool. In the picture to the right, you see each stick corresponding to one horse. By examining the collection of sticks in hand, one knows how many animals should be present. You can imagine the usefulness of such a system, at least for smaller numbers of items to keep track of. If a herder wanted to count off his animals to make sure they were all present, he could mentally and methodically assign each stick to one animal and continue to do so until he was satisfied that all were accounted for. Of course, in our modern system, we have replaced the sticks with more abstract objects. In particular, the top stick is replaced with our symbol 1, the second stick gets replaced by 2, and the third stick is represented by the symbol 3. We are getting ahead of ourselves here. These modern symbols took many centuries to emerge. Another possible way of employing the tally stick counting method is by making marks or cutting notches into pieces of wood, or even tying knots in string, as we shall see later. In 1937, Carl Absalom discovered a wolf bone that goes back possibly 30,000 years. It is believed to be a counting device. Another example of this kind of tool is the Ishango bone, discovered in 1960 at Ishango and shown below. It is reported to be between 6,000 and 9,000 years old and shows what appeared to be marking used to be done for counting of some sort. Spoken words, written numbers, are just a few examples of early methods of counting and simple symbols for representing numbers. Extensive books, articles, and research have been done on this topic and could provide enough information to fill this entire course if we allowed it to.